In this set of videos, we will introduce the kinematic motion model for our robot. This overview can be considered your Introduction to the Bicycle Model 101. After we cover the representation and controls of our model, we will look at a few types of problems we can solve. Along the way, we will derive all the formulas needed to solve these problems. Finally, we'll go through an example to solidify our grasp of the material. Let's dive in. Our typical robot is represented by a car, which has 4 wheels. The side view and bird's eye view, or overhead view, are here. The arrows are included to indicate the direction of motion. Instead of deriving the kinematic formulas for a 4-wheeled vehicle, we will use a 2-wheeled vehicle, which approximates the 4-wheel model and makes the calculations easier. This motion model is known as the bicycle model. The bicycle model has 2 controls, the steering angle and the forward movement. The steering angle is defined by the angle that the front wheel makes with the orientation of the vehicle. If the wheel is turned to the left, then this will be a positive steering angle. The right will be a negative angle, and straight ahead, or parallel with the orientation of the vehicle, will be a 0 steering angle. The forward movement control will move the robot from one point to another. It is measured from the rear axle at the start of the movement to the rear axle at the end of the movement. Note that the rear axle is fixed and that it is not allowed to swivel like the front axle. It will always be parallel to the orientation of the robot. The robot pose consists of 3 properties. The location of the robot makes up 2 of these, X and Y position. Theta gives the orientation. In this picture, robot A and C both have the same orientation. Similarly, B and E have the same orientation. Robots D and E have the same position. None of the robots have the same pose. Using the bicycle model, we can choose to engage only one of the controls. In this case, if we keep the steering angle fixed at 0 degrees and only apply forward movement, then the robot will travel in a straight line in the direction of its orientation. In this simple case, what will the final pose of the robot be? Since the orientation is parallel to the x-axis, the forward movement will only affect the x property of the pose. In this case, the final pose will be x equals 12, y equals 2, and theta equals 0. Here is another example of applying a forward movement. What is the final pose of the robot? Since the orientation is parallel to the y-axis, the forward movement will only affect the y property of the pose. In this case, the final pose will be x equals 2, y equals 12, and theta equals pi over 2. Those examples were easy because all of the forward movement was attributed to a particular axis, namely x or y. This was because the robot's orientation was parallel with either the x or y axis. When the robot is not parallel with either axis, then we need to use trigonometry to determine the result of applying the forward movement. In this case, what is the final pose of the robot? The final pose is x equals 7, y equals 10.7, and theta equals pi over 3. To get this, we can multiply our forward movement distance by sine of the orientation to get the change in the y direction, and multiply by cosine of the orientation to get the change in the x direction. Now a question about the intuition of this bicycle model. Imagine that the robot was traveling on a surface which left a track behind it after the movement. Will this movement produce a single track or 2 distinct tracks behind the robot? Assume we are using a bicycle model which has 2 wheels, not a car which has 4 wheels. The answer, which may seem obvious, is a single track. What happens when we engage both controls in the bicycle model, the steering angle and the forward movement? If the robot uses a positive steering angle, like the one shown here, and travels in a forward motion, what shape will be generated by the track left behind? Although we all love robots, the answer is not a heart, unfortunately. The correct answer is a circle. Now one more piece of intuition before we talk about the problem we can solve using both controls. will there be a single distinct track or two tracks left behind if we engage in this compound movement involving both the steering angle and the forward movement? This may come as a surprise to some of you. In this case, there will be two distinct tracks. Both will be circles, and in fact, they will have the same center point. The smaller circle will always be made by the rear axle, and it is this one we are concerned about for this lesson. So what can we do with this compound bicycle model? Given an original pose and a set of controls, we can determine the new pose after applying these controls. If the robot starts here, using a constant fixed steering angle, and travels forward by some known distance, then we will be able to determine the new XY location, as well as the orientation of the robot after the motion. We will walk through the derivation of the equations in detail, but first, here's an overview of the steps involved. First, we will determine the radius to the center of the circle. Then, we will determine the location of the center of the circle using the radius and robot orientation. The center of the circle will serve as our reference point. Using the distance traveled, we will determine the turning angle around the circle. Finally, we will determine the offset using the original orientation and the turning angle. So, the first question I have to test your intuition is what happens to the center of the circle as I increase my steering angle. As I increase my steering angle, the center of the circle becomes closer to the robot. Here are a few examples to demonstrate this. Robot A has the smallest steering angle. Robot B has a slightly larger steering angle, C an even larger steering angle, and D has the largest steering angle of all. As you can see, as the steering angle increases, the center of the circle moves closer to the robot. Note that the circle we care about is the one made by the rear axle. In order to determine the final pose after the compound movement, the first step is to determine the radius. We can do this using trigonometry. We can create a right triangle using the line seen here. The two which meet at the center of the circle are perpendicular to the front and rear axles. The third line goes through the two axles. Because both lines from the center are perpendicular to the axles, we know that these angles here are right angles. The steering angle, alpha, which is given to us, is labeled here. This means we also know that the angle in the triangle here is pi over 2 minus alpha. This means the last angle in the triangle is alpha. Since this side of the triangle is known, the length of the robot, we are able to determine the radius to the rear axle using the tangent of alpha. Here is our formula. Rearranging terms, we can see that the radius is equal to the length of the robot over the tangent of alpha. Next, we will determine the location of the center of the circle. We will create another right triangle here. This time, the hypotenuse is known. It is the radius found in the last step. Also, the angles of the triangle can be determined by using the fact that we know this angle here is a right angle. This angle is also known. It is the orientation of the robot. This means the angle here is pi over 2 minus theta, and the final angle here is theta. Using sine and cosine, we can determine the lengths of the other two sides of the triangle. Finally, to get from this point to the center, we see that we need to go in the negative x direction, as indicated by this displacement vector here, and in the positive y direction, as indicated by this displacement vector here. Therefore, our final formula for the location of the center of the circle is center x equals x minus sine theta times radius, and center y equals y plus cosine theta times radius. So here's another test before we move on to the next step. Given what you know so far, what distance must the robot travel in order to return to its current position? Assume a fixed steering angle is used. we can see that to get back to the original position, the robot must travel all the way around the circle. Doing so requires the robot go a distance equal to the circumference of the circle, 2 pi r, where r is a radius we found by dividing the length of the robot by tangent of the steering angle. The distance between 2 points along the edge of a circle is called the arc length. The formula to determine the arc length is the central angle times the radius. We are using beta to represent the central angle. In our case, we have the arc length and the radius, so when we rearrange terms, we end up with beta equals the arc length over the radius. Note that this formula is exactly how a radian is defined. When the arc length is equal to the radius, the central angle is 1 radian. Since we are given the forward distance, and we have already calculated the radius, we simply divide these values to determine beta. Finally, we will determine the final location by calculating the offset from the center of the circle using the central angle we just found. Here again, we create a right triangle. We know the hypotenuse is the radius, and this angle here is theta plus beta. Using sine and cosine, we can calculate the x and y offset. We see that we need to go in the negative y direction, so we subtract this distance from our center point, and we go in the positive x direction, so we add this distance in the x direction. This leaves us with our final location formulas. Our new x is equal to center x plus sine theta plus beta times radius. Our new y is equal to center y minus cosine theta plus beta times radius. And now the final piece of the puzzle. The only thing left to find is our new orientation. Remember, orientation is the direction the robot is facing with respect to the positive x-axis, this angle here. We know this is a right angle, and we know the angles for this right triangle, which means our final angle here is just beta plus theta. So here you have it, all the formulas we just derived. You may combine these to get rid of any intermediary variables. Now using these formulas, we will walk through an example. Assume you are given this information. What is the ending pose of the robot after carrying out this compound motion? Only round the final result. You can round it to the nearest integer. If you perform the calculations correctly, the right answer will jump out at you, almost as if you knew it from the start of the lesson. So for this problem, we were given the length of the robot as 0.2, the steering angle as 0.166, the distance traveled as 1.07, the XY location of the robot as 0.118 and negative 0.54, and finally the orientation of the robot as 0.1. If you use these exact values and don't do any rounding throughout all the calculations until the very end, then you will end up with the final pose is 101, the X position is 1, the Y position is 0, and the final orientation is 1. Congratulations! You made it through the Bicycle Model 101 lesson. Not only do you know about the bicycle model's kinematic motion formulas, but you also know how to derive them yourself.